Welcome to my video course on railway safety and systems engineering. We rely on complex railway networks every single day to move millions of people and massive amounts of freight. But here's the hard truth we face as engineers. In dynamic, complex railway operations, zero risk is a total myth. It simply doesn't exist. So how do we design systems that stay safe while keeping society moving? Well, we use a highly structured mathematical approach to manage the unknown.
Here's our roadmap for today. We're going to cover the risk assessment process, likelihood and severity scales, building the risk matrix, principles of risk acceptance, and finally the ALRP principle.
Section 1. The risk assessment process.
You know, we hear the words hazard and risk thrown around interchangeably in everyday life, but in safety engineering, they are vastly different concepts. A hazard is literally an accident waiting to happen. It's a dangerous state, like an exposed electrical wire or a fast-moving train that's just waiting for a trigger event. Risk, on the other hand, is a strict mathematical calculation. It is the exact combination of the likelihood that the harm actually occurs, multiplied by the severity of that harm.
To manage these elements out in the real world, our engineering process has to be strictly linear. First up, we systematically identify every conceivable hazard. Second, once those hazards are identified, they are analyzed to determine the exact level of risk they present to the railway, the staff, and the public. And third, we apply control measures to knock that risk down to an acceptable level. This isn't guesswork, it's a highly rigorous framework.
Section 2. Likelihood and severity. The first axis of our risk calculation is likelihood. Basically, this refers to how often a hazardous event is actually expected to occur. It's categorized using terms ranging from frequent, meaning it's likely to occur annually, all the way down to improbable, which means it's unlikely to happen even within 100 years. We map this on a 1 to 5 scale to establish an objective baseline. It gives us a really solid temporal gauge for expected trouble. The second axis is consequence, or severity. This measures the actual degree of harm resulting from an accident. The scale ranges from negligible, which would be a non-reportable injury or a minor scrape, up to catastrophic, signifying multiple fatalities. Just like likelihood, this also runs on a scale from 1 to 5. By isolating this severity metric, we can objectively measure the absolute worst-case scenario.
Section 3. Building the risk matrix.
So by plotting our 1 to 5 likelihood against our 1 to 5 severity, we build what's known as the risk matrix. This table classifies risk into 3 distinct zones. The red zone is intolerable. If an activity falls here, it's simply not permitted, period. The yellow zone is tolerable, meaning we can operate, but we absolutely must actively reduce the risk down to ALRP. And the green zone is negligible or low risk, where we basically just maintain our current controls.
Let's ground this theory in reality for a second. An unprotected level crossing is the perfect example of an accident waiting to happen. The trigger event? A car pulling onto the tracks just as a high-speed train arrives. Because a collision here easily hits that catastrophic severity level, engineers use the matrix to mandate strict controls, things like building a bridge or installing automated barriers. That drives the likelihood way down and keeps train movement safe.
Section 4. Principles of risk acceptance. We have to acknowledge that some risk is inherently acceptable in complex operations. But because public perception of risk can be incredibly inconsistent, we can't just rely on gut feelings. Instead, risk acceptance is determined based on strict, objective baselines. We look at national legislation, industry codes of practice, and standardized societal norms. These frameworks provide a definitive target for what is legally and socially acceptable.
Section 5. The ALRP principle. ALARP stands for as low as reasonably practicable. What this fundamentally dictates is that risks must be reduced until the cost of any further mitigation becomes grossly disproportionate to the safety benefit it provides. It's a vital concept because it forces us to step out of the purely theoretical realm and directly weighs safety gains against hard financial and practical realities.
When you look at the framework of tolerability, there's a really clear hierarchy. At the top, risk is totally unacceptable. Down at the bottom, it's broadly acceptable. That vast middle region, that's the ALARP zone. As engineers, our job is to continually drive risks downward through this tolerable zone, implementing safety mitigations until we hit that exact breaking point where further costs become completely unreasonable. And this creates the core tension of any cost-benefit analysis. We are constantly weighing the safety benefit, which is the hard mathematical reduction in potential fatalities and injuries, against the financial cost of actually building those engineering controls. To legally demonstrate that a system is safe under ALRP, we have to definitively prove this mathematical balance.
But you might be wondering, how do you mathematically compare human lives to engineering budgets? Well, we use a comparable fatality score, or CFS, to standardize all levels of harm. Mathematically speaking, one fatality is equivalent to 10 major injuries, which equals 100 minor injuries, which equals 1,000 negligible injuries. I know it sounds a bit cold, but converting human harm into calculable numbers is the only way to ensure consistent, objective safety standards across the entire network.
Once we have that CFS, an independent monetary value is assigned to it. Typically, at a national level, one comparable fatality score is valued between 1.5 and 2 million British pounds. This allows the system to objectively determine if a massive safety upgrade, say a multi-million-pound bridge, is statistically justified, or if the financial cost is genuinely grossly disproportionate to the actual safety gained. I want to leave you with a bit of a provocative thought here. If engineering absolute 100% safety would financially bankrupt the entire transit system, how much risk are you personally willing to accept for the sheer convenience of modern travel? Assigning a financial threshold to human safety is definitely an uncomfortable reality, but it's the exact compromise that allows our complex world to keep moving forward. So, to quickly summarize, engineering safety requires us to first identify and analyze hazards. Next, we plot them on the risk matrix using likelihood and severity. And finally, we mitigate those risks aggressively until we reach the ALRP threshold, balancing human safety with practical costs. That wraps up our deep dive into the risk assessment process. Thanks, we can see you in the next video.